Hi everyone, my name is Marcio Batista and this video is the second part of my talk for the event Geometric Analysis Past, Present and Future Season 2. In the first part of the talk, I presented some notations, some important results in the literature, and also recall very important functions associated to immersions uh, of hypersurfaces in the Euclidean round sphere. Okay. Now I will continue to introduce notations, and next of it I will present a nice functional, and such functional will help us to produce a nice test function, and such nice test function will allow us to deduce that does not exist minimal, compact minimal two-sided hypersurfaces in the projective space with scalar curvature constant scalar curvature, and the index equals to 2. Okay, this is the main result of this talk. There does not exist compact two-sided minimal hypersurface with constant scalar curvature in the projective space with index equals to 2. Okay, let's start with the first slide. In this slide, I give a motivation for the functional that we will introduce now. If you recall from the first part of the talk, in the last slide of the first part of the talk, I presented the expression of the quadratic form associated with the second variation applied to the vector field phi AB. Okay, the expression is very simple. It is the integral of the normal square of the Vanguard operator minus n, all this expression, times the sum of the function f8, the angle function associated to the direction A square, minus the high function in the same direction square. Okay, and such expression is interesting for us because if you do a very simple variation of that expression, we will obtain a nice functional. Such functional can be defined in this way. Okay, this functional f here. This functional acts on the cylinder of lambda, a cylinder over lambda. The cylinder is lambda times r, where lambda is this manifold SO n plus 2 times the sphere. Such lambda is a manifold, and our functional given by this expression, beta integral of this expression, is a smooth functional, and it is related with the index of the vector fields phi AB. If you put here psi equal the identity and beta equal 1, you have exactly the expression of I apply in psi AB. Okay. Next, we'll observe that this functional has nice properties for our purposes in this talk. So, the first interesting property is the following. If you have a critical point of this functional, then the integral of this expression is the norm square of the Vanguard operator minus n, all this expression times G A naught. Such integral is equal to 0. In particular, such function j will have zero mean if the scalar curvature of sigma is constant. Observe that if the scalar curvature is constant, then by the Gauss equation, the norm square of A is constant too. And such expression, norm of A square minus n, is constant, and the integral becomes just the integral of GA naught times this number, norm of A square minus n. Okay? And if such a number, norm of A square minus n, is not 0, then the integral is 0. Okay? But what is happening if the norm of A square is equal to n on sigma? We have a beautiful result of Chern, Ducarmo, Kobayashi, which says that the manifold is congruent to the torus, the Clifford torus. So this case is not interesting for us. We can assume that the norm square of A is different of n. And in such condition, we have this function GA naught with 0 mean. Okay? But I would like to point out that the importance of the critical point of F. Such critical point help us to produce a function with 0 mean. Next, I noticed that if sigma is minimal and it has constant scalar curvature, then the first eigenvalue of J, of the Jacob operator, is negative. Okay, and the eigenfunction associated to it is the function constant equals to 1, for example. So the second eigenvalue is associated to a function of 0 mean. Okay, so maybe the function GA naught can help us with a function associated to the second eigenvalue. Okay. So after this observation in the previous lemma, we are interested in guarantee the existence of critical points of F. For this, we use a minimax argument. So we consider the number m1. The number m1 is equal to sup of inf of the function f in a special class of series. Okay, this sup is take on the class of maps which are homotopic to this explicit function phi naught. Okay, phi naught is just the inclusion of the lambda manifold in the cylinder. Okay, we observe in a in a direct way using the expression of the functional f, that such number m1 is well defined. Is a number, okay, and such number is non-positive. Okay, these two things are interesting for us because, in general, in the theory of minimax, the infimum of a sup of or a sup of an infimum in general is a critical point. So this guy here, M1, is a candidate to be a critical point for the function f. So such number is well defined. We'll use it later. Let's continue the talk. Now I recall an interesting principle, minimax principle. This minimax principle is for finite dimensions, and it is very simple to present. You assume that you have a complete Riemann manifold and just smooth C1 functional on sigma, which satisfies the Palais-Meil condition. I will tell what it means Palais-Meil condition in a few minutes. Okay. Also, suppose that the collection of sets which is invariant with respect to any smooth semiflow psi stays invariant by A. That means that A applied to psi is a non-decreasing function, and apply the sets of f in f. Okay. Two more conditions on the semiflow is psi is the identity in the beginning, and psi is always homeomorphism of sigma. If you fix the parameter t, psi with this parameter fixed, t fixed, is a homeomorphism of sigma. Okay? So in such conditions, if beta is defined by this expression infimum of the sup in this family, okay, the family F, then the number is finite, and also it is a critical point, a critical value of E, okay, of the function E. Okay. So if you compare with the definition of M1, it is very similar, okay? Of course, if you look carefully, you will see the expression of M1. You have a sup of an infimum, and in the theorem you have an infimum of a supremum. Okay, but it is just technical. You see in the next slide that it's not a problem. Okay. So in the next slide, we have a consequence of this minimax principle for our functional f. The corollary says that if f are functional, defined a few slides before, if f satisfies the Palais-Meil condition, then the number m1 is a critical value of f. This is an immediate consequence of the previous theorem. you can define the functional E in this theorem as minus f, and all the conditions here are verified for this functional, and so you can apply the theorem and deduce that the number, the minimax number, is a critical value of the functional minus f. And in an obvious way, if beta is a critical point of the minus f, then minus beta is a critical point of f. Okay. So the number m1 is a critical value if the functional satisfies Palais-Meio condition. We don't know if f satisfies the Palais-Meio condition, but we will argue in two parts. In the first part, we will use if f satisfies Palais-Meio condition, you can argue in some way, and if f not satisfy Palais-Meio condition, you will argue in another way. Okay, let's continue. So here I recall what it means Palais-Meio condition. Palais-Meio condition means if any sequence going to infinity has image bounded by the function e, and the gradient of the function e applying this sequence goes to 0, then the sequence admit a convergent subsequence. Okay, it's a very simple condition to say. Okay, so let's announce our main result in this talk. The main result is this in this slide. There is no connected, compact, two-sided minimal hypersurface of the real projective space with constant scalar curvature and Morse index 2. Okay? In particular, in this class of hypersurfaces, you have a gap. You know that the totally geodesic spheres and the Clifford torus has index 1, and so if you assume constant scalar curvature, the next possible index is 3 or more. Okay. The proof is more or less simple, because what we have to do is to use a special test function to get one new direction where the stability condition, the index will be nice. Okay, let's do it. Consider an immersion of sigma in the projective space with the conditions of the theorem. So if you are able to lift x to a map x tilde, such mapping x tilde gets sigma into the sphere, this is possible in some situations. Okay, you have direct conditions to guarantee in which conditions you can lift a map. if you in this condition to you you can lift the map x to a map x tilde, then the lifting map is will be compact to side minimal hypersurface with constant scalar curvature and index 2. But it is not possible because L-Sophie proved that the index is greater than n plus 3, in particular is always greater than 2. Okay, so cannot lift the map X. This case is not possible. So if you cannot lift the map X, you can do another argument to lift a new map. Now the map you lift is not X anymore, but a new map from a special cover of sigma to the sphere. You consider P a cover of the hypersurface sigma, the double cover, and you consider the lifting of X composed with these two cover of sigma. In such conditions, we are able to lift such map X composed to P to a map which will take sigma hat into the sphere, and such new map X hat satisfies this condition: pi compose x hat is equal to X compose P. Okay, if you do a picture of these maps, you have a diagram. Such diagram commutes. Okay. Notice that X hat is a connected compact two-side minimal immersion with constant scalar curvature. Okay. It is occurs because the metric in sigma hat is the metric induced by the projection P, and you can put now a metric in the lifting in such a way that the lifting is isometric immersion, because the maps commutes as I have said before. Okay. Next, denote by sigma the involution associated to the projection to the two cover map P. Okay, involution is a diffeomorphism in sigma hat that changes the fibers of the map P. Okay, if you compose in the right side with the map X hat, we obtain minus X hat. It's a direct condition because sigma permutes the fibers. So consider N be a unit normal vector field along sigma hat, and use again that sigma, the derivative of sigma does not preserve orientation, to deduce that N composed to the involution is equal to minus N. Okay? And finally, we denote a function which is invariant by sigma as an even function. Invariant means that f composed to sigma is equal to f. Sigma, the little sigma, the involution, okay? So, in this setting, we take the map X to the projective space and lift it to a new map from the two cover of sigma in the sphere now. And if you look to these two maps, you have a two vertical maps associating sigma hat to sigma and the sphere to the projective space. Such diagram commutes. So in this configuration, in this setting, we know that the first eigenfunction is 1 because we are assuming that the scalar curvature is constant, so the Jacobi operator is just the Laplacian plus a constant. Okay, so the first eigenfunction is equal to 1. And the second eigenfunction is negative because we are assuming that the index is equal to 2. Okay? If the index is equal to 2, then this second eigenvalue is simple 2. Okay? We denote by f2 the eigenfunction associated to lambda 2. So, it's a very simple computation using the definition of index that if you take any even function which has mean 0 and is perpendicular to f2 in the L2 norm, the L2 inner product, then the quadratic form I applied to u is greater than or equal to 0. And the equality occurs if and only if u is in the kernel of the Jacob operator. Okay, it is a direct computation using just linear algebra. It's nothing more than that. Okay. The second lemma is a lemma inspired by the ideas of Ducharme, Ritoré, and Royce, and in such setting, we are able to prove that this map G, big G, defined by this expression is just the mean of a vector function with f2. This integral, not a mean, but just the integral. You don't divide by the volume of sigma hat. But this integral is a linear isomorphism. Okay, the idea is very similar to the idea of Ducharme, Ritoré, and Royce in the paper. Okay. And the last lemma that we will need is the following. If you assume that exist two vectors in Rn plus 2 with a naught non-zero in such a way that the mean of the map phi a naught b naught is equal to 0 and phi a naught b naught is perpendicular to f2 in the L2 inner product, and also the quadratic form I applied to phi a naught b naught is equal to 0. In such conditions, the manifold sigma hat must be locally congruent to the Clifford minimal hypersurface. So it is very rigid, but we are assuming that the phi a naught b naught is not is in the kernel of the J operator. If you read carefully, the three first conditions imply that the phi I naught b naught is in the kernel of the J operator. So it's a very, very nice property. So let's provide the proof of the main theorem. We have two cases to analyze. The first case is when F satisfies the Palais-Mail condition. In this situation, you can deduce, you announced this early, that the integral of this function, normal of a squared minus n times ga naught, is equal to 0 for a critical value of f. Notice that if f satisfies the Palais-Mail condition, m1 is a critical point, so you take this term, this triuplo, c naught, a naught, beta naught, is a critical point of f. In such critical point, this integral is 0. So, if you observe, this means that the function g a naught has mean 0, because the first part of the integral is constant. So the map g a naught has 0 mean. And associated to this a naught, you can take a b naught using lemma 2, because the mapping j big is an isomorphism from the Rn plus 2 in itself. Then you can find b naught in such a way that these two conditions in the last line of the slide holds, is true. Okay, so to use the last lemma of the previous slide, we have to compute the quadratic form I applied to this field, phi a naught b naught, and prove that its value is 0. So, if you compute, you have this expression. Okay, this is a simple expression. And if you rewrite the expression in the first equality, you notice that appears the mean of GA naught. And the mean of GA naught is 0. So this inner product is 0 too. So in this situation, we are able to apply lemma 3 and conclude that the hypersurface sigma hat is locally congruent to the Clifford torus. But Clifford torus has index equal to 1. Sorry. Sigma hat has index different to 2. Just see it. Okay? So, in this situation, we get a contradiction. So, the final case is when f does not satisfy Palais-Mail condition. In this situation, we have a sequence going to infinity. Infinity in the cylinder is the third coordinate goes to infinity. And the gradient of the functional f along these sequences goes to 0. Okay. After a tedious computation, we have this expression. This expression is very, very nice for us. This expression is very nice for us. You can rewrite the integral of the norm square minus n times GA using the derivatives of the functional f. And using such expression along the sequence, we deduce that this integral is very small all along the sequence. So since lambda, big lambda, is compact, we can assume without loss of generality that the Pcj and Ij, which belongs to SON plus 2 times the sphere, converges. So if you take the limit in the expression in the second line, we deduce that the integral of the function norm of a square minus n times ga is 0 too. So we found a vector in the sphere such that the function ga has mean 0. And in this situation, we are able to repeat the computations in the first case and get a contradiction again. Okay? So, in both cases, we proved that there does not exist a hypersurface with index 2. Okay? In this way, we deduce the theorem, the mean theorem. Okay? I conclude my talk with that. Thank you very much for your attention, and I hope to see you soon.